vital importance is to know the complex number equivalent of some standard loci, which we have already studied in coordinate geometry. So I'm going to give all of those here. I'm just going to go through them on a trot, because it's not as important as some other topics in complex numbers, but then they are still important, and so we must be aware of them. Equation of the line passing through 2 points is, so suppose we have a line which is passing through the points z1 and z2, then the equation of the line is given by this determinant, which has z bar 1 on the first row, z1 bar 1 on the second row, z2 bar 1 on the third row is equal to 0. On simplifying, we'll get z1 bar minus z2 bar into z minus z bar into z1 minus z2 plus z1 z2 bar minus z1 bar z2 is equal to 0. Now we can substitute a bar as z1 bar minus z2 bar and substitute a bar as a as just z1 minus z2, so that it's z bar, and so it's going to be z bar over here and not over there, plus b, which is z1 z2 bar minus z2 z1 bar. This gives us the general equation of a straight line which is passing through the points z1 and z2. So the slope of the line a bar z plus az bar plus b is equal to 0 is given by a plus a bar divided by I into a minus a bar. Now a plus a bar is the negative of the real part of a and divided by imaginary part of a. So thus equation of a line which is parallel to the line a bar z plus a z bar plus b is equal to 0 is given by a bar z plus a z bar plus lambda is equal to 0, right? Should not be the same constant, it should be another constant, just like in straight lines. Next, equation of a line perpendicular to a bar z plus a z bar plus lambda is equal to 0 is given by a bar z minus a z bar plus I into lambda is equal to 0. Equation of a line passing through 2 points. Now, if we are given the equation of a line and if we are given the complex number corresponding to a certain point, what would be the shortest distance between that point and the line? It's given by, say, ZC is the complex number from which we are trying to find the distance. ZC A bar plus ZC bar into A plus B divided by 2 times of the magnitude of A. This is the distance of that point from the given line. Condition for 4 points z1, z2, z3 and z4 to be concyclic, given by argument of z4 minus z1 by z2 minus z1 plus argument of z2 minus z3 by argument of z4 minus z3 is equal to pi. Okay, so what does it say? The opposite angles add up to pi, and thus it is a cyclic quadrilateral. Now, perpendicular bisector of a line segment joining z1 and z2 is given by modulus of z minus z1 is equal to modulus of z minus z2. Next, if we are given 2 points z1 and z2 given by a and b, then what is the locus of a point joining z1 and z2? Well, it's given by distance between z minus z1 plus z minus z2 is equal to, we know that p lies between z1 and z2, so z minus z1 plus z minus z2 is equal to distance between z1 and z2. So this is the equation of the locus of a point between 2 points z1 and z2. Next, equation of an ellipse is given by magnitude of z minus z1 plus magnitude of z minus z2 is equal to a constant k. The constant k, of course, has to be greater than z1 minus Z2, modulus of Z1 minus Z2. What are Z1 and Z2? They represent the foci of the ellipse. So here PA plus PB is the constant and the locus of Z is on the ellipse. And we can find the eccentricity of the ellipse by substituting Z1 and Z2 in the formula magnitude of Z1 minus Z2 upon magnitude of Z minus Z1 plus magnitude of Z minus Z2. That is magnitude of Z1 minus Z2 divided by the constant K. Next, equation of the hyperbola is given by modulus of Z minus Z1 minus modulus of Z minus Z2 is equal to a constant K, which has to be less than the modulus value of Z1 minus Z2. And the eccentricity of the hyperbola is given by modulus of Z1 minus Z2 by the constant K. Now, how do we write the equation of a circle in the diameter form? If the extremities of the diameter of a circle are given as Z1 and Z2, then we can write the equation of the circle as modulus of Z minus Z1 the whole square plus modulus of Z minus Z2 the whole square is equal to modulus of Z1 minus Z2 the whole square. Okay, that's basically the statement of the Pythagoras theorem written in complex number form. And the simple equation of a circle is given by Z minus Z1 modulus is equal to K into Z minus Z2, right? And the locus of the segment of a circle, which has Z1 and Z2 as two endpoints, is given by argument of Z minus Z1 by Z minus Z2 is equal to alpha, where alpha is the angle subtended by this point, any point Z through the arc AB, where A is the point Z1 and B is the point Z2. Next, if argument of Z minus Z1 by Z minus Z2, where Z1 and Z2 are two complex numbers representing 2 points, if this is equal to either plus pi by 2 or minus pi by 2, then we can be sure that the locus of Z is a circle with Z1 and Z2 as the endpoints of its diameter. Okay, in a similar manner, if argument of Z minus Z1 by Z minus Z2 is equal to 0 or pi, then the locus of Z is a straight line passing through Z1 and Z2. Finally, modulus of Z minus Z naught is equal to alpha bar Z naught plus alpha Z naught bar plus R divided by 2 alpha. The locus of Z is a parabola whose focus is Z naught and directrix is the line alpha bar Z plus alpha Z bar plus R is equal to 0. The point Z in the complex plane satisfying modulus of Z plus 2 minus modulus of Z minus 2 is equal to plus or minus 3. Now, comparing this with a very familiar equation, Z plus Z naught minus, or rather Z1 minus Z minus Z1 is equal to a constant. So therefore Z1 is equal to 2. So we get Z1 minus Z2. So this is, say, Z2, and Z2 is equal to minus 2. Z1 minus Z2 is equal to 2 minus minus 2, so that's equal to 4. And 4 is greater than 3, right? So the condition is that the constant should be less than Z1 minus Z2, in which case it will be a hyperbola. And here it is found to be true, so therefore this equation represents a hyperbola. So therefore the point Z lies on a hyperbola. Option D.